Hello, everybody. Hope we're all doing well. Yes, we're starting to get close to seeing the light at the end of the tunnel. 2 more weeks. That's it. Can you believe it? Anyway, I just want to go over this homework. This should have been a relatively easy homework for everybody. It really isn't all that difficult. Let's take a look and see what's going on here. So, you had to watch this little minute physics video. It asks what happens when light travels through glass, water, or other transparent material. And basically, it bends when it changes material. Now, I added a note on here. It only happens true when the light is incident oblique, not 0-degree angle. In other words, and let me draw it up here. If let's say I've got a block of glass, and I've got light going into that glass. Yeah, if it comes in at some angle like this, it is going to bend. However, if the light beam comes in square into the material, that would be 0 degrees because we always measure from the normal, it's not going to bend. It goes straight in, okay? So just be aware of that, all right? If it's going to come in at some oblique angle, it's going to bend going to the new material, provided there's a speed change. If there is no speed change, it's going to go straight in there. Okay, so it bends, and I wrote that down. This is only true if the light's incident at an oblique, not 90-degree angle. What happens to the speed of light when it enters water compared to air? It will slow down. Now, it says here, label the wavelengths of the wave in air and in glass. Well, here's a wavelength right here. However, there's a wavelength here. There's a wavelength here. And then there's your wavelength right there. Okay, so you can see the wavelength got shorter over here. As the light slows down from air to glass, what happens to the wavelength? It gets shorter. Frequency does not change once a wave is made unless there's a Doppler shift. So please be aware of that. What happens to the color of the light? It stays the same since the frequency determines the color of the light. Frequency does not change as you go from one material to the other. Okay, unless there's a Doppler shift. And we'll talk about that a little bit later on because you can have a Doppler shift with light. Okay, what determines the energy of the wave? The frequency. Now, you're not going to have to do this because we're not going to get to modern physics. But just so you know, the energy is equal to Planck's constant times the frequency. Okay, that's Planck's constant. You're not going to have to do this because I don't think we're going to get to modern physics. But just so you've seen it somewhere, and that's the energy on a little bundle of light. It's called a photon. Now, why does light slow down in glass compared to the air? The light acts like a particle and interacts with the atoms in the glass. Basically, it gets caught up in the atoms. It gets absorbed and released, and that slows it down. In between the atoms, it's going to travel at the speed of light. Okay? Diagrams from the video. Constant C, according to physical constants. What is it? C is the speed of light in a vacuum, and it's 3 times 10 to the 8th meters per second. All right? If you take it to 2 sig figs, it's 3 times 10 to the 8th. And you can see it getting caught up here inside of the atoms, all inside of there. Okay, that's straight out of the video. Can anything travel faster than the speed of light? Absolutely not. Einstein said it's impossible, and so far we've not found him to be wrong. Even though there were some experiments where they got a number greater than that, it turned out to be wrong. Okay? Define the index of refraction. It's basically the speed of the light in a vacuum divided by the speed of light in whatever that new material or medium is. N equals C over V. N is the index of refraction. It has no units because it'll be meters per second over meters per second. Speed of light in a vacuum is C. That, of course, 3 times 10 to the 8th meters per second. That's a constant. It's not going to change. V is the speed of light in a material, in the medium. Now, you were asked to rank the indices of refraction for most solids, liquids, and gases from lowest end to highest end. Low is going to be gases, which means it's going to be the fastest in the gases. Remember, a low N means a high speed. In the middle are liquids, and at the top, at high indices, are solids. The atoms are packed more tightly together in a solid, and they tend to interact with the photons a lot more and tends to slow things down quite a bit more. Now, there's our index of refraction. It's on the second page of the reference table, depending on what order you printed the thing out in, but it should be on the second page of the reference table. And here's a listing of the indices of refraction. Using the video, calculate the index of refraction of quartz. If the speed of light moving the quartz is 2.05 times 10 to the 8th meters per second. Well, indice equals speed of light in a vacuum divided by the speed of the new medium, N equals 0V, and you get 1.46, and it has no units to it, okay? Does it have units? Note they drop out. Meters per second divided by meters per second, they're going to drop out. Using the video, calculate the speed of light as it travels through a diamond. N equals 0V. Algebraically rearrange this, put the C below the N, and I just switched to two sides. There's my speed in a vacuum. There's my index of refraction. And I get 1.24 times 10 to the 8th meters per second for that speed. All right, here we go. Now this one, what's the speed of light in flint glass? Show or work, including equation and substitution with units. I kept the V equals C over N because I worked it out before. I take a look on my reference table, which I conveniently have right here. Flint glass has got an index of 1.66. That means it's 1.66 times slower in that material than it is in a vacuum. V equals C over N, 3 times 10 to the 8th meters per second, divided by 1.66 equals 1.81 times 10 to the 8th meters per second. And guys, that is it. Shouldn't have been a hard lesson for you. I wanted to keep it pretty easy because of APs. The one that's due on Monday is more difficult, so don't wait till the last minute to do that. That's dealing with refraction and bending of light. And please use your protractors for the diagrams that I asked you to on those particular questions. There are 3 questions plus the example that was done within the lesson. You've got to use your you have to use your protractors in order to draw those things out accurately. All right, that's it. Everybody be well. Hope your families are doing well. Hope you're doing well. I know it's been a long time, but there is light at the end of the tunnel. All right, take care. Bye-bye.